My name is Asteris Apostolidis, and I want to welcome you to the 29th session in our series for AI for Aviation Sustainability. Please note that this webinar is being recorded. Today's presentation is called Thermodynamics of Metaheuristics. In an inversion of roles, the presentation today will be given by our esteemed host, Jeroen Mulder. Jeroen works for Air France-KLM Technology Office and has a background in mathematics, operations research, and data science. Now, before we start, some house rules for this webinar. Any question during the presentation can be addressed through the Q&A section inside the BlueJeans interface. The moderation today will be done by Maria Vencher and me. We will address all your questions at some point through the presentation and at the end of the presentation. Now it's time to give the floor to Jeroen, so please be seated.
Okay, thank you very much, Astrid, for giving me this opportunity. Really great to be on this side of the camera. First challenge for today is to see if I can share my screen. I guess it should be working, but maybe you can tell me if everyone sees the screen.
It's on. Yes.
Perfect. Okay.
Great.
So
we can start then.
Okay, perfect. Thank you. So the presentation is called Thermodynamics of Metaheuristics, and it's linked to sustainability because one way of being or becoming more sustainable is to reuse best practices with respect to the way you are coding. And nature, for example, is a great source of inspiration for such best practices. And reusing best practices for your algorithms is what mathematicians call metaheuristics. And in this presentation, we will look at how nature can help to solve our optimization problems. And that's the part where thermodynamics is coming in. Today's presentation has a subtitle, From Hot Problems to Cool Solutions. And the reason for that is that the presentation is about temperature and how you can measure the temperature of your algorithms and use it to better control it. My objective for today is to explain you how you can measure this temperature of your algorithm in such a way that when you start solving your problem, the temperature is still high, and when you come to a possible solution, your temperature should be low. And then in this presentation, the two fields of thermodynamics and metaheuristics will come together. And some parts, sorry for that, of the presentation are quite technical and detailed. So what I would like to do is to start with a kind of high-level storyline in which I explain to you which steps I will take in the presentation, and then in such a way that you can understand the basic ideas behind the approach. So first I will describe the steps, and then later I will go into the messy formulas. So my first step, first I will start explaining how you can measure the temperature of a gas. That's the thermodynamics part. Second step, I will explain how you can gasify your algorithm. And then using this gas example, I can explain or will explain how you can measure the actual temperature of your algorithm when you are solving the problem. The proof of the pudding is in the eating, so I will show you that this empirical temperature, as I can define it, makes sense for algorithms like, for example, simulated annealing. And then in the end, I will show you how you can take out the guess of these algorithms again, leading to a kind of general notion of temperature for any iterative algorithm. And then this temperature should be used to control your algorithm in a better way. And then as a cherry on the cake, I will show you where the gas is and where the temperature is when you are trying to solve Sudokus. So that's basically the high-level storyline. So if at some moment during the presentation you are lost, then at least you know in which step you are lost. Okay, to begin with, I will show you a short video with an example from nature showing you why temperature is a logical indicator to look at. And see if I can get this started. Okay, so this is a short movie about magnetism and the effect of temperature. The example is about heating a magnetic metal rod. And at some moment, the metal rod loses its magnetic properties and will not be magnetic anymore. Then after a short time, during which the rod is cooling down, the magnetic properties will return and the rod becomes magnetic again. And what you will see in this example is that when cooling down, the magnetic dipoles inside the metal are realigning again, and below a certain temperature, they are fully aligned, making the rod magnetic. And this is nature's way of finding optimal configurations with the least energy. and it can be considered as the way nature solves optimization problems. So that's at least what you see in nature and what we would like to understand in more details. To do so, we will look at a more simpler example from nature and try to understand it in more details. And that's about cooling down gases. So when you have a heated gas and you release it and set it free in space, its molecules will spread and fill the space. After some time, the gas molecules are all over the place and the gas temperature will have adapted to the temperature of the system. So in that case, we say that the gas has reached an equilibrium and it has adapted to the system temperature it's exposed to. Here it's important to notice that this equilibrium is not a static one. It's a dynamic one in which molecules will still move around, still move, let's say, between energy states. And each such transition will cause small fluctuations in some properties of the gas. And what turns out is that from these fluctuations, we are able to determine the temperature of the gas. I will show that in more details later on. But these state transitions will cause small fluctuations in, well, the energy of the gas and the so-called entropy of the gas. I will come back to that later. So these small fluctuations near this equilibrium turns out to have a fixed ratio. And this fixed ratio, when this gas is in equilibrium, will fluctuate around the system temperature. So it behaves like a temperature. And for that reason, we call this ratio, as I will show you later on, the empirical temperature. Okay, so I promised you some frightening slides. So here's the first one. So it might look frightening, but the idea is that I'll explain you more precisely what I just told you about these small fluctuations and why they do have this fixed ratio. So I will simplify the gas example a bit more. So there are only two energy states. So the first one is called E0. So let's say with energy E0, and this energy is less than E1. And the temperature, so the gas is exposed to a system temperature T. We just said that, so you expect that after some time, those molecules will spread, and all those molecules, or most of them, will be in the lowest energy state. Well, most of them, not all. So I will not show you, but only tell you what you can learn from thermodynamics about the behavior of this gas, when you, let's say, are near this equilibrium. So you can compute the percentages of those distribution. How many molecules will be in the E0 state and how many will be in the E1 state. So based on this temperature T and the values of E0 and E1, you can exactly calculate how many gas molecules will be in E0 and how many in E1. And this calculation, quite complex, but it's based on the famous Gibbs-Boltzmann distribution, as you see over here. And it's a distribution, good to make that remark, it's a distribution that prefers the lower energy state. And well, here you see the expression for these probabilities. So the probability of E0 is what you see over here. So an exponential and then an expression in E0 and T. And the same thing for, let's say, the E1. And you divide by, let's say, a quantity Z. It's called the partitioning function. And basically it's used to normalize these probabilities so that in the end, when you add them up, it should be 1. So what I said, a lot of formulas, a lot of information, quite theoretical. So these probabilities are the theoretical ones based on this distribution. And in the end, so when you have an actual gas and it's spreading around, let's say it's not always this theoretical result. It will be close to, but it will not be the same. So this actual distribution, this empirical distribution, will be different for two reasons. First reason, I think that's well, understandable. The first reason is that your gas only consists of a finite number of molecules. It's a huge number, but it's finite. So it means that the theoretical values will not be achieved because it's finite. So these empirical values or probabilities will be approximate. That's the first reason. The second reason, also the one that I already noted, so the equilibrium that you have is a dynamic one. So there are always molecules moving around, going from one energy state to another energy state. So it means that your empirical distributions will always change for each of those transitions. There's one molecule going from one state to another. So the energy will change, and also your distribution will change. Okay. In this case, in the empirical distribution, the expressions are simpler. Basically, you have, let's say, n molecules, of which n0 are in the energy state E0, n1 are in the energy state E1, and then basically it's just making the ratios. So the empirical probability for E0, that's just n0 over n. And the empirical distribution probability for E1 is just n1 over n. And in the end, approximately, it will be equal to what the Gibbs-Boltzmann distribution is saying. So these expressions with exponential in there. Perfect. What I said before is that when, let's say, when you have a molecule going from one state to the other, there are still quantities that will change. Just try to understand exactly which quantities are changing and if we can understand the behavior. So first of all, the gas molecule is going from one energy state to another energy state. So it means that the expected energy of the gas will change. Well, that's an expression that you see in the first line over here. So that's the expected energy. And basically, it's the value of the energy times the ratio of this energy. So it's E0 times the ratio belonging to this state, the N0 of N, plus the value for, let's say, the E1. So it's E1 times the N1 over N. I hope that one is clear. So that's the expected energy. What we saw before is that with each transition, the energy will change, but also your empirical distribution will change. So you would like to have kind of a similar formula, similar quantity for your probability, for your distribution. So you could try to use the expected probability. Sounds a bit strange, but let's try it. So you would say have the value for your probability times the ratio. So for the E0, that would be N0 of N times N0 of N, plus the same expression for the E1 energy state. Okay, well, nice formula, but sorry for that, it's not working. And why is it not working well? The reason is that if you look at the expression for energy, it's an additive formula. It behaves additive. And if you look at this expected probability expression, it behaves in a multiplicative way. And that's not what we want. It can be quite easily fixed. So if you have something that, let's say, is behaving in a multiplicative way, you just take the logarithm and it behaves additive. Well, since probabilities are values between 0 and 1, you don't want to have, let's say, if you take the logarithm, it becomes negative, and you would like to have a positive value. So what you do is you take minus the expectation of your logarithm of your probability. Sounds complicated? It's not that complicated because it's just an expression that you can calculate. So if you have this actual gas, if you have these numbers n0, n1, and n, you can just compute it. So this expression that you see over there is just, let's say, the value, so the logarithm of n0 over n times the ratio n0 over n. And then the same thing for n1. So the logarithm of n1 over n times n1 over n. And well, I promised you something about entropy. Well, this quantity with this definition is called the entropy. And yeah, I will come back to that later in the slide just to explain a bit why it's called entropy. But basically, what you see is that if you look at the laws of thermodynamics, you can look at these quantities, and near equilibrium, it turns out that, let's say, small changes in expected energy and entropy behave, let's say, in a proportional way. So basically, for each transition near equilibrium, it turns out that the change in the energy, the expected energy, is proportional to this change in entropy. So that's something you can show, let's say, using the laws of thermodynamics. I will not do that. I will, let's say, look more at the experimental result and try to show you the same thing. Yeah, but in the end, it means that the ratio delta E over delta S behaves constant. And what is nice, and I'm not sure if we have people in the audience that, let's say, have a bit of background in the thermodynamics, but this type of ratio is well known in thermodynamics. It's used as the formal definition of temperature. So it follows that this kind of empirical ratio behaves temperature-like. And that's the reason why we call it empirical temperature, because it's based on the empirical distribution of the energy states of those gas molecules. Okay, so this is, let's say, the formal definition of empirical temperature. And basically what I promised you before is to show, let's say, one easy picture, I hope, about the entropy. So in the previous slide, we saw the formal definition, the formula. So sometimes that's not really helping you. So I hope that this picture is more helping you. So on the left, what you see is a picture with a lot of chaos or a lot of disorder. These kind of systems have a high entropy. And it's also corresponding to the formula that we saw before. And let's say if you look on the right, it's well ordered. There's no chaos at all. These systems will have a low entropy. So basically, let's say on the left, if these are gas molecules, they spread all over the place. That's high entropy. And if it becomes more ordered, then the entropy is becoming lower. Check. A lot of theory, a lot of thermodynamics, a lot of statements that I did not prove, because I think it's easier just to see if you can understand this from actual computations. So let's say leave behind the frightening part and try to make the example as concrete as possible. I will try to do some calculations and I'll try to explain what I did. So we looked at the cooling down process and we tried to simulate it in Excel. Or at least we tried to do the calculations in Excel. So I choose some values. So in this slide, you see that for E0, I took the value 10. For E1, I took the value 50. And for the temperature T, I took the value 10. For the number of gas molecules, I took N equal to 400. So I'm quite sure that it's not representative for real gas. But Excel doesn't handle the big numbers like the Avogadro numbers quite well. So just stick to the 400. Okay, what did I then do in Excel? So I started with those 400 gas molecules. I started with 300 gas molecules in the lowest energy state, and I had 100 in the highest energy state. Then what you do is you just pick one gas molecule at random, and what you do is you check whether it's in the lower energy state or in the higher energy state. And if it's in the higher energy state, you're quite sure, for 100%, that it will move to the low energy state. You go always from, let's say, the high energy state to the lower one. If the molecule was in the lower energy state, it should prefer to stay there, but due to, let's say, kinetic energy, internal energy, there's still the possibility that it will, say, move to the high energy state. And this probability to do so, that's determined by this Gibbs-Boltzmann distribution, the one that we saw in the previous slide. Okay, so this is then, you pick one gas molecule, you check where it goes to, also with the probability, and after each, transition, you can then recalculate both the expected energy and also the entropy. And that's quite easy. There's only one molecule moving. So the computations are quite simple. It's something you can do quite easily in Excel. After calculating the energy and the entropy, you can look at those values from the previous state, the previous transition, and you can calculate the deltas. So based on that, I'm able to calculate this ratio delta E over delta S. And I will do that many, many times. Then let's say you get a lot of lines, you can make a graph on it, and that's basically what you are seeing here. So in the graph, I plotted this ratio delta E over delta S, the temperature. And what you see there, if you start, let's say, at a high value, it's about, let's say, 36, the first iteration. And then what you see is that at some moment, it converges to this system temperature of 10. So from these experimental results, and of course, it's not a real formal proof, but it makes sense to say, okay, this ratio behaves like a temperature, so we call it the empirical temperature. What I also did, so what you also see in this graph, is a small table. Let's say the last line of this table says the distribution based on the Gibbs-Boltzmann, and the lines above is more what your simulation is doing. So you see that most of the gas molecules are in the lowest energy state, and only a few are in the highest energy state. Yep. So that's, let's say, calculations. Try to, let's say, do the simulation in Excel. And what we just did was we modeled the physical cooling down process as an algorithm. We found that 98% of the cases, the gas molecule ends up in the state with the lowest energy. In 2%, or only 2%, it ends up in the state with the highest energy. And as a next step, if you are near this equilibrium, you could maybe lower the system temperature a bit, and then wait again to equilibrium, and then repeat many times. And then at some moment, let's say both the temperature of the system and the empirical temperature will become 0. And then your hope is that all the molecules will be in the lowest energy state. The algorithm that I just showed you, what you actually can do in Excel, and that, let's say, describes this cooling down process, it's called simulated annealing. And in this case, you solved a very easy problem. We only had, let's say, two values, the E0 and the E1. And well, this algorithm figured out which is the lowest of both. But the nice thing is that this approach, it can serve as a template to solve other more difficult minimization problems, optimization problems. And you can use it like that to solve things. And why is that interesting? Well, these non-exact algorithms are useful because optimization problems are not always solvable. So sometimes you cannot solve them exact because it's either taking too much time or the solution is just not known. And what you then see is that you rely on kind of ad hoc methods, heuristic methods, a kind of advanced trial and error approach. And these you call heuristics. And in case your heuristic, like let's say the simulated annealing, is generic enough so that you can reuse them, you will call them metaheuristics. And the one that we just saw is, let's say, based on the cooling down of gases. Another one that should be maybe even more familiar, it's the way that, let's say, humans solve Sudokus. And I will try to come back to that example later on. And also here you see that many of those metaheuristics are based on what you see from nature. So that they have, well, I call them funny names, but let's say a lot of metaheuristics have names like simulated annealing, iterated local search, variable neighborhood search, but also things like evolutionary computations, genetic algorithms, particle swarm optimizations. So the fact that these metaheuristics, these well, say design patterns are based on what you see in nature, it gives you a more confident feeling that it's really sensible to reuse them. Check. So there's a kind of general structure of those metaheuristics, and I'll try to explain this structure a bit more detail. So what I said before, it's trial and error. You try to reuse it. So this general structure looks a bit like what you see over here. So you start your algorithm, you create your initial solution, or you create a set of initial solutions, and then based on that, you try to update this set of solutions, either only the initial solution, or let's say the set of initial solutions, by looking at, let's say, neighbors of this states. So you try to improve your solution, try to improve the set of solutions. And what you then see is that at each step you try to calculate the fitness of your solution. You try to see, okay, is it still good enough? So for example, the energy could be a good measure for the fitness of your solution. And then you try to see whether it's good enough or not. If not, then you, well, iterate more and more and more. And you do this many times. There are some challenges for this. So this is a kind of ad hoc method to do so. And you have a lot of questions. So how many iterations should you take? How are you sure that you really found, let's say, the right solutions? So one of the main questions is, okay, how can you be sure that you really look at the full solution space? So if you have a kind of heuristic where you say, okay, I have a solution, I'll try to improve it. How are you sure that you really searched into your whole solution space? Nice one. Also, how many iterations should you take? So how many iterations do you take before you terminate your algorithm? What kind of indicators can you use here to detect that you could terminate, or that maybe you should, let's say, change some of the settings and then continue iterating? What also is interesting, and it's what we saw before in the simulated annealing approach. So what we saw is that, well, you are not sure that there's some kind of randomness in your heuristic. So how do you deal with this randomness? So different runs might have, let's say, different solutions. So it also means that you will not always find the best solution. How do you deal with that? So basically, that's what I will try to, let's say, describe now. So it's what we said in the beginning. So I explained to you the measuring of the temperature of a gas. The other one that I promised you was to, well, have a gasified version of your algorithm. And basically that's what I'm trying to show you over here. So if you look at those challenges, what you could do with your metaheuristic is to run it in a kind of gasified version. So first question is, so how does your gas differ from a set? So in the previous scheme, or the scheme that you are seeing here, you start with an initial set of solutions. Well, if you take a really big set, what is different from a gas? So approach to, let's say, have a gasified version of your metaheuristic is to start with a really large set of solutions. If you do that, it's not, let's say, a guarantee, but it's exploring more of your solution space. So if you only have, let's say, one single solution, initial solution in your set, you will not really explore everything. But if you have thousands or even more of, let's say, those initial solutions, you're more likely to really explore your solution space. So that's the thing that we would like to do here. The nice thing, if you have this gas approach, so a lot of initial solutions, and you try to, let's say, pick one of those solutions, try to update things, then let's say you can compute of each solution the energy, and also, let's say, the energy of this solution. Based on that, you can compute again the expected energy of your gas and also the entropy of this gas. And then gas not in the sense of, let's say, the molecules, but the gas of initial solutions and the solution that you try to improve on. So if you have energy and entropy calculated, and you compare it with, let's say, the previous transition, you can compute again the deltas, and based on that, you can compute empirical temperature. You can put it back in your feedback loop, and then what's nice, so if you look at this scheme, you see that you will start with a lot of initial solutions. Based on that, you can compute empirical temperature. So really looks nice, but what actually do you do to gasify your heuristic? So what I tried to say before is that, if you run things as a gas, so you have this gas of solutions, one way of gasifying your heuristic is just to pick one solution of the gas, and then on this solution, you apply your heuristic. So heuristic could be, let's say, an ordinary one, where you only have, let's say, working on one initial state, or let's say one solution. You can gasify it by running, let's say, many solutions at once, and then just picking one, applying your heuristic, put it back into the gas of solution. So you apply your heuristic to the solution, and you can update the gas. And, that's nice. So what I showed you, let's say a basic scheme or a general scheme to, gasify your heuristic, where you can compute the empirical temperature. And then I think the first question is, okay, that's nice, but what does it measure? So does it make sense to compute empirical temperature in this way? Well, first answer, if you do this for, let's say, simulated annealing, the answer will be yes. So what we just saw before when we looked at the gas example, where we, let's say, had the same approach. So you pick any solution from the gas. Based on what we saw with this Boltzmann or this Gibbs-Boltzmann distribution, you can compute this acceptance probability. And basically, if you pick any solution from the gas, you can apply, let's say, your simulated annealing approach. So you try any neighbor of your solution that you picked, and you accept it with this probability. You put it back in the gas. And what's then nice is that if you look at this scheme, you have, let's say, a kind of system temperature in your acceptance probability. So there's a kind of steering temperature that you use in your heuristic. You also see that, let's say, you can calculate energy entropy, so you can calculate empirical temperature. And then what's nice is that near equilibrium, turns out that your empirical temperature is, approximately equal to the temperature that you are steering with. So I showed you how you could, let's say, gasify your metaheuristic. I showed you that you can then compute an empirical temperature. And I showed you that it makes sense for, let's say, gasifying your simulated annealing because, the empirical temperature and the steering temperature are, approximately the same. And in fact, there's nothing that you need to prove over here, basically, because, it's just the gas example. So if you really understand the gas example and how you can measure the temperature of the gas, and then this is almost for free. Okay, this was, let's say, the tough part, or the toughest part. I promised you also some fun part about solving Sudokus. So that's the part I will now start with. But maybe, for me, just to take a breath, maybe, Astrid, are there any questions so far in the audience?
No questions so far, Jeroen, but I would like to invite the audience to ask their questions, maybe now. Or maybe, later during the presentation. Before going there, we can give you 30 seconds to to get the breath. There is a question. So let's see. All right, from Stefan. Question. It looks like the Monte Carlo method with a specific estimator. How this method compare with the Monte Carlo one?
That's a question I don't know the answer yet. So that's something to look into. So I know, let's say, the Monte Carlo simulation, and probably this is maybe a more advanced Monte Carlo simulation with this estimator, but I will need to look at, let's say, the more details about it. So basically, let's say I came from the angle of thermodynamics, and I found, okay, if you look at this gas example, you can do things for, let's say, your metaheuristics in general. What I see, I think that's then also the link. So you could also rephrase this more in, let's say, the statistical approach. Basically, you have let's say, probability distributions that you are updating, and I think everything that I'm showing here is in fact about probability distributions. But I think most people already find metaheuristics quite complicated. If I make the mix of metaheuristics and also the probability or the statistical part, I think it would be quite complicated, but it's a good question. So I will try to look into it.
Okay, thank you very much, Jeroen. Yes, all right. So, no other questions so far. You might want to continue, and then we can gather all the questions in the end and have them answered by you.
Okay, perfect. So until now, let's say I showed you how to measure the temperature of a gas. I showed you how you can gasify your algorithm and then measure the temperature of your algorithm. But let's say the gasified version. Well, I think if you look at what you do in practice, in real life, for example, when you solve Sudokus, it's maybe a bit different. So try to look at the example of Sudokus. I'll try to, well, look together with you what people do when they solve Sudokus, and I will try to see, well, where the gas is in this example, in this way of solving Sudokus, and also, let's say, where then the temperature is coming from. First of all, just to be sure, so what are Sudokus? So short reminder, this is the explanation. So it's a puzzle, it's a 9x9 grid in which you have to fill in the values 1, 2, 3 until 9. There are constraints, so in each row you should have all the different values. In each column you should have all the different values, and each of those boxes that you see should also have the 9 values. There are many ways, of course, of doing this when there are, let's say, when all the fields are empty. So each puzzle that you see has some preset values. And these are set in such a way that there's only one solution. And the challenge is to find this one solution. And it's based, let's say, on the values that are given. The complexity of the puzzle can be, well, very easy to extremely complex. And this, in the end, should be, let's say, then the answer of this Sudoku. In fact, this was a quite easy one. First of all, so before we were talking about optimization problems, so why am I now talking about Sudoku? So what's the link with solving optimization problems? Well, in fact, what you're trying to do is you try to fill in as much as possible empty cells with values that don't conflict with these constraints. So that's it. You would like to minimize the number of conflicting constraints. Minimizing a number, that makes it an optimization problem again. So given the fact that you have, let's say, this puzzle or this setup with constraints, you are looking for a solution with no conflicting constraints, makes it into an optimization problem. And in fact, there are two objectives for your optimization. So you are trying to reduce the number of conflicting constraints, but you're also trying to reduce the missing information. So you start, let's say, with this grid, many empty cells. So in the end, the goal is to have all cells filled in, so no missing information, but also no conflicting constraints. So with each step, you try to reduce the number of conflicting constraints. So read like you try to minimize the energy, and you also try to reduce the missing information. You have to read like you try to reduce the entropy. And well, just look at this example. So what most people do when they try to solve the Sudoku is not to fill in all the fields and then check the constraints. That would be rather stupid. So what most people do is they try one of the cells and try to figure out which values could be there. So it's a kind of trial and error approach, and you try to see, say, what the constraints would say about the values that you have over here. So if you, for example, look at the first row and you look at the second cell, basically what you see here is that, well, in this row you see that the 1, 3, 7, and 8 are already used. So it means that if you look at the still possible values in the second cell, so the possible candidates, it's only 2, 4, 5, 6, 8, and 9, because the other values are not possible anymore. And I see I made an error there because the 8 should not be in there. So excuse me for that. So that's, let's say, for the row constraint. You do the same thing for, let's say, this constraint. So you see that the 4, 5, and 6 are already used. So they should not be used in the list of candidates. So also you skip them from there. And then if you look at this box, you also see that 8 and 9 are already used, meaning that you can also remove them from the list of candidates. So basically, in the end, you only end up with, let's say, one possible value in your list of candidates. So that's easy. This value, this cell should be a 2. What you can do for, let's say, the third cell is the same process. So looking at the row constraint, looking at the column constraint, looking at the box constraint, and you will find out that there are, say, 2 values still possible in this field. You can do it for all the cells. So just iterate through all the cells, have the same approach. And then basically you find this kind of overview. So for each cell, you have a list of candidates, possible candidates. And from here, you try to, let's say, do the next iteration. So you try again to start with the cell. You look at the row constraint, the column constraint, the box constraint. And in each step, you try to derive more information about the list of candidates. So you started with, let's say, cells in which you have, let's say, only one value. What you then did, you say, okay, I won't look at only the value, but I will look at the list of candidates. And you're trying to, translate the simple constraints into kind of higher order constraints on the list of candidates. You try to use those constraints to eliminate candidates from the list. And you have all kinds of nice names for that. So what we just saw before with the 2. So you have a list of candidates with only one value. That's called a naked candidate. And sometimes you have 2 cells with only 2 values. That's called, let's say, naked pair. You also have things like hidden candidates. And I think I also have an example of that one. So if you look at, let's say, the first row again, and you look at the 5th cell, you see that the list of candidates is 5, 6, and 9. What's nice there, so if you look at this cell, so you look at the constraint imposed by this row, you look at the cells, the other cells in this row, and you look at the list of candidates. And what's nice, if you take the join of these lists, then what you see is that you have, let's say, the collection or the set 1, 2, 3, 4, 6, 7, 8, 9. Meaning that the 5 is not used in these other cells, implying that if you take the complement of the list, that's 5. It means that in this cell that you picked, the value 5 should be there. Okay, so I think that's still, I hope, clear enough. What's nice to notice is that in this case, you were not even looking at the list of candidates of this circled cell. So you were only looking at the cells in the remainder of this constraint. And only doing it like this, so either using the naked candidates or in this case the hidden candidates, is not always enough. So if you have, let's say, only cells like this, I think it's a very, very easy Sudoku, but in general it will be a bit more complicated. I also have a example of this. So sometimes you need more information than only the list of candidates. And you need to know how certain you are of some of those candidates in the list. So for example, if you look at the block at the left bottom, so here you see 3 cells that are not completed yet. And what you see is that you have 2 cells, the 2 cells on the bottom, in which, let's say, the candidate 7 is used and it's not used in the other cell. So from this you can derive that, let's say, in those 2 cells, either one should have the value 7. Those 2 cells also belong to the column constraint. So if you look at this one, you see that in this column, those 2 cells, you are certain about the value 7. Meaning that if you look at the other cells in this column constraint, the 7 cannot be used. For example, pick this cell. So you see that the list of candidates is 1, 7. The 7 cannot be used. So basically, if you look at the other, let's say, values, the other list of candidates, and you use the fact that you are certain about the 7, it means that you can remove the 7 from this list of candidates. And in the end, you will have the value 1. That's nice. So again, and I think that's the point I'm trying to make here. So we started with the list of candidates, and we saw that sometimes it's not enough information. So in this list of candidates, you would like to, let's say, make it a bit more advanced. You would also like to have information about how certain you are about some of those values. Well, in fact, that's probability distribution. So you have a list of 1, 2, 3 until 9. And for each of those values, you indicate how certain you are about this value. So it's a more advanced list of candidates. It indicates the certainty that you have about those values. And then what we saw before, so we were joining lists. Basically, you can now add the probabilities. So if you look at the column constraint that you had before, you take, let's say, the cells outside the cell that you picked, and you just look at the probability distributions for each of those cells, and you can just add it. And then, well, taking the complement in this case means that you are looking for the entry with the minimal entry. So for the candidate with the minimal value over there. I will try to, let's say, come back to an example a bit later, but basically the way people solve Sudokus is looking at a random cell, looking at the different constraints, trying to derive information. So for let's say, the list of candidates, you try to have also the certainty in there. So basically you have probability distributions in here. So the scheme that you then have for your heuristic would be something like, okay, you start. So you initialize all the empty cells of your Sudoku as we just did before. We try to update the Sudoku by just picking any empty cell of the Sudoku. And we try to, well, look at the constraints, row constraint, column constraint, and the box constraint. And we try to, well, have more information in there by looking at the other cells in the constraints, looking at the probability distributions, adding those distributions together, and then look for the values with the lowest probability, and then update, let's say, the probability distribution of the cell that you started with. So basically, this is kind of heuristic, a kind of, let's say, ad hoc approach that seems to be working. Maybe not all the times, but maybe it's good enough. And basically, if you do it like that, then you can calculate let's say, the constraints or the conflicting constraints again of your updated Sudoku. So in some way, you have, let's say, the fitness of your Sudoku again. So this scheme looks a bit familiar. It looks like, let's say, the scheme we had before for the metaheuristics. Only what you see, what you are missing, is the part about well, the energy, the entropy, and then also empirical temperature. So would there be a way, in the way you solve Sudokus, to really, well, calculate the energy and the entropy, and also the empirical temperature to, well, by considering it as a kind of gas? That's something that you can do by, well, having the approach that we saw before. So you have a heuristic, you have an approach that seems to be working. You could try to gasify it. What does it mean if you gasify it? So you take many instances of the same Sudoku, then you pick any one from the gas. So you have this gas of Sudokus, you pick any instance of it. So that's a Sudoku on which you can then, let's say, apply your heuristic. So you update this Sudoku based on your logic and you put it back in the gas. If you do it like that, you can, let's say, compute the energy, you can compute the entropy, and you can also compute the empirical temperature. But, well, gasifying a Sudoku like this is not very practical. So when we look at what we did before, so where is the gas coming from? Well, if you think about that, we saw that for each of those cells, we had a list of candidates. So you have these probability distributions for each cell. In fact, it's a kind of gas. So what you could do, you could look at all those cells, all those probability distributions, and you could take in some way the product of these distributions. And then you would have an overall distribution for your Sudoku, for your gas of Sudokus. And you could use that to compute the energy, the entropy, and then also compute the delta, so the empirical temperature. That's an approach that's working. So basically, you could visualize it like this. So you have this gas of Sudokus. You take one, based on your heuristic, you pick one cell, and you know from the gas of Sudokus that there's a kind of underlying distribution, underlying probability distribution for this cell. And basically, what you then try to do is you try to, well, look at the candidate cell, try to see what the probability distribution would be, and this is a kind of way of factorizing the gas of Sudokus. So it's considered as a product of those distributions. You can express the global energy so of the gas into, let's say, the terms of the probability distributions. You can do the same for the entropy. And in that way, you can compute the empirical temperature of your Sudoku solver. So I hope, well, things are still clear. Basically, what I was saying is that if you look at the way we solve Sudokus, we do it with list of candidates with probability distributions. if you take the product of all those distributions, it makes a gas. Based on this gas, you can compute an empirical temperature. Oh, that's cool. Well, cool. Almost cool. So you can solve Sudokus, you can compute an empirical temperature, but then the next question is, okay, but where is the steering temperature? Where is the system temperature for your Sudoku? Because it only makes sense to talk about an empirical temperature if there's some system temperature to which you can compare it. So the question is, can we steer by a kind of external system temperature? Well, perhaps we could use this Gibbs-Boltzmann trick again. So what we saw before in our heuristic is that we sum the probability distributions, and then you look for candidates with the least value. So if you remember what I told you at the beginning of the presentation, so simulated annealing, using the Gibbs-Boltzmann distribution, they would prefer values, or let's say the minimal values, states with, say, the least energy. In this case, you have, let's say, a probability distribution, you have the candidates 1 until 9, and you basically are looking with, let's say, the one with the least value over there. So what we could do here is use the trick that we saw before by adding those probability distributions, applying this Gibbs-Boltzmann trick, and then basically you would end up with a kind of new probability distribution, and that would be, let's say, the one that you would use for your picked cell. That algorithm, or let's say that approach, is a familiar one. So it's not new that you use it for your Sudoku solving. It's called mean field annealing algorithm. And it's called mean field because, let's say, the cell that you picked, you don't use the candidate list in there. You are only, let's say, using the ones that are, let's say, based on the constraints. And this mean field annealing algorithm means that in the end, so I will first, let's say, show you this example. I think that's important. So try to make it a bit more concrete. So if you look at the example that we had before, you have this first row again. You have this number 5 in there that we saw that we could compute because it was a hidden candidate. Basically, if you look at the description that I just gave, and so you look at the first cell over here, there's the value 8. So in terms of probability distribution, it means that you have a factor within the 8th position, the number 1. If you look at the second cell, it's, let's say, a list of candidates with only the 2. It means that, let's say, your probability distribution is 0, 1, so that's in the second position, and the remainders are also zeros. If you look at the third cell, so you have the 2, 4, and 6, so 3 values. Well, let's assume that they have, let's say, equal probability. Then you have, let's say, 1/3 in the second position, you have 1/3 in the 4th position, and you have 1/3 in the 6th position. It's the same for, let's say, this cell, and so on and so on. You don't look at the cell which is circled, because you are only looking at, let's say, the remainder in the constraint. If you add these together, you have something like 1, 8 over 3, 1, and so on. And that's not a probability distribution, because if you add up the values, it's not 1. But basically, if you look for the candidate in here with, let's say, the lowest value, this one. And basically, the 0 is on the 5th position, meaning that the 5 indeed is a hidden candidate. You will not always be that lucky, so sometimes it's not a 0, but let's say it's a bit more than 0. And the approach that we just described with this mean field annealing is that you look for the values that have, let's say, the least probability in there. And that's, again, the mean field annealing approach. And that's where, let's say, the Gibbs-Boltzmann distribution is used. So it computes the probability for this vector, so for the sum of probability distributions. And basically, it's then, let's say, a way of normalizing, and you use that to insert in a value for the cell number 5. Okay, so I have still 9 minutes. I still have, let's say, one frightening slide a bit. Basically, what I try to explain here is how it would look like if you describe it in mathematical terms. So the first step is that you sum lists. So you have an expression like this. So this value CKL, that's, let's say, that's the value of a cell in the kth row in the 11th column. And there, let's say, you have 9 entries. So that's what's the A indicating. There are some weights over there. And basically, the weights count the number of constraints on the cells. So if you have cells in the same row, then there's one constraint. So the weight is 1. If you have cells in the same column, then let's say the weight is also 1. If you have cells in the same block, it's also like that. If you have cells that are not related to each other because they are not the same constraint, the weight is 0. Also, let's say the weight for the cell with itself is also 0. So that's the way to ensure, let's say, that the candidate list of this 5 is not taken into account. So that's summing of the list. You can use the Gibbs-Boltzmann to, let's say, do this kind of normalization again. And this one is preferring the values with the lower value. You can also have this partitioning function again to normalize things. And basically that's, let's say, what the algorithm is doing. So how does your algorithm look like? I will try to not hurry up because I think that's not what I should do. Basically, so you start with initializing all the empty cells with Sudoku. You pick this empty cell. You update the cell with this transfer function that we just described by adding, by summing, then by applying the Gibbs-Boltzmann distribution, and then by putting it back. Based on that, you can calculate the fitness of your updated Sudoku, and then you can calculate entropy of your Sudoku, and you can calculate the deltas. And in fact, the computation of the deltas is quite easy because there's not a lot of things that you should compute. So if you look at the whole Sudoku and you try to compute, let's say, the number of conflicting constraints, the energy, the entropy, basically, because you're only changing, let's say, one cell, the computation itself will be quite simple. So what I call it's global versus local. And so global is, let's say, do the computations for the whole gas. Local is the fact that you only have to look at one particular cell because that was the one that you were updating. You put things back again, and then you terminate at some moment. And what's nice, and what should not be a surprise because I think that's what my presentation is about. In fact, if you compute, let's say, the empirical temperature in the way I described here, so based on the gasified approach where you take the product of the probability distributions, then it turns out that this empirical temperature is approximately equal to, let's say, the steering temperature. So in this transfer function where you apply the Gibbs-Boltzmann distribution again, there's this temperature T. And in the end, so when you, let's say, reaching the equilibrium again, you will see that this empirical temperature and this temperature are almost the same. Okay, so a lot of storytelling. I hope things are still clear. Just to give some proof, so I, let's say, implemented this mean field annealing for Sudoku in, let's say, Excel. Here you see a graph that I made for the steering temperature. So basically that's coming from the Gibbs-Boltzmann distribution, and it's this blue line. And well, I did the computation, so I computed the empirical temperature, and it should be no surprise, but it's almost the same as the steer temperature. It's lagging behind a bit, and in the end you see it's almost identical. So basically what I'm showing here is that you can compute the empirical temperature, the temperature of your solving of the Sudoku, and it's really, say, close to the steering temperature. So it means that you could use this empirical temperature as a kind of feedback mechanism. So at some moment you try to decrease your steering temperature, and you can do that based on the empirical temperature that you at that moment are calculating.
Sorry, Jeroen, I was going to say that your sound was really not good, but just for 30 seconds. But it's okay now. Good.
Okay. Yeah. So okay. I hope I'm there again. So last slides. So question is, okay, so for this Sudoku that we can solve, I showed you how you can compute the empirical temperature. I show you how you can, let's say, also do some kind of system or steering temperature in there. And I showed you that it's almost the same. So that's nice, but what does it give you? So how can you use it? Well, my point is that these concepts from thermodynamics give you some more feeling, some more information about the way you are solving your problem. So idea is that you could use quantities, indicators from thermodynamics to assess whether, let's say, your solution that you found is really the global optimum or maybe it's a local optimum. How could you do that? So let's say one approach would be to use these formulas again. So sorry again for the formulas. But basically what we saw before is that you have this kind of partitioning function. So this set that you were using to, let's say, you normalize the factor, the sum of all those entities. You can, let's say, express that in terms of your entropy, your expected energy, and your temperature. And that's coming from thermodynamics. So I will not show you. You could try to do the calculations yourself. It's quite fun. But what you see in this last formula over here is that the logarithm of your partitioning function, you can express it like the entropy minus the expected energy over T. And what's nice there is that, well, in case you found your solution, your entropy will be almost zero or will be zero. When you found, let's say, a global optimum, at least for the Sudoku, you are sure that there are no conflicting constraints. So your expected energy will be zero. So in that case, if you look at this expression, you will find out that, let's say, the logarithm of this partitioning function should also be zero. In case you found, let's say, a non-global optimum, so a local optimum, then this expected energy will not be zero, because, well, it's not the global optimum, and there's only one solution for your Sudoku. So this will have a kind of positive value, meaning that this expression would be negative, meaning that, let's say, the logarithm of this partitioning function would also be negative. And that's something that you could use. So if you look at this graph, so this is the graph I made for a Sudoku that I was able to solve with my mean field annealing. There you see, let's say, the energy. So that's the orange line. You see the entropy, that's the blue line. And then you see also the logarithm of the partitioning function computed using the formula that I showed you before. And you see that here at some moments it's a kind of, it's becoming stable. At some moments it's dropping to zero. So here you see that all the three quantities are quite close to zero. If you do the same kind of graph for a Sudoku that was not solved, then you will find this kind of graph where you see that, let's say, it's almost similar. But what you see is that at this moment, the purple line, so the logarithm of the partitioning function, is a bit shaky. It goes then to zero, but it also drops below zero. And this is an indication that the solution that you are working on is not an optimal one. I have 1 minute left for my conclusion. Well, I'll just, let's say, show you the slide. So first of all, recap of the storyline. So I try to explain you how you can measure the temperature of a gas. So I think that's the high level storyline. I try to explain you how you can gasify your algorithm. And then based on those two, how you can measure the temperature of your gasified algorithm. So that's cool. Also showed you how you can take out the gas again and then see that you can, let's say, get this mean field annealing approach. And my conclusion is that, well, empirical temperature gives better control for annealing metaheuristics. So for all other heuristics, I'm not sure yet, but at least for annealing metaheuristics, you see that it makes sense to use the empirical temperature. What's nice is that solving Sudokus is an example of this mean field annealing algorithm. And what's also nice, I think that's then, let's say, the link back to, let's say, the first example that I showed you. So spontaneous magnetization below a certain temperature is also something that you can explain by this mean field annealing approach. And I have more slides, but it's not for now. So I would like to ask the moderators if there are any questions from the audience.
You know, Jeroen, I was expecting the questions, but people are so much hanging on your lips, as we say in Dutch, that I think they even forgot to ask it, and or you are so clear and obvious. So it's 5 o'clock. I would like to invite the audience, if you have a question, please do it now. And otherwise, I think I will give the word to Asteris to close. So Asteris, yeah, please jump in and then we can conclude. And Jeroen, it was perfect. We enjoyed your enthusiasm. Dank je wel.
You're welcome.
Okay, thanks, Maria. Hi again, everyone. Thanks, Jeroen, for this very, very interesting presentation. Well, I'm really happy that you addressed this topic. I have, well, maybe some questions, but given, looking at the time, I don't think we can spend much time on questions anymore. But well, maybe a question that links a bit what you presented with, let's say, the general theme of this series of web lectures. So, in the end, how do you think the model you presented contributes to well, sustainability in general, or maybe aviation sustainability more particularly, given the problems that we, try to solve in the aviation domain?
So for the aviation domain, I'm not quite sure, but what I started with, so reusing best practices, I think is something that, let's say, makes you more sustainable. So don't try to, well, start with all kinds of algorithms from scratch. try to see how you can reuse things. And the fact that you have these kind of best practices or design patterns for your algorithms also is ensuring that you have better code. So if you really apply this kind of template for your code, it's helping you. One of the things that I saw with the simulated annealing is that in a lot of literature, it was not clear what kind of indicator people should use to really determine whether they should terminate, go to the next iteration or not. And in fact, what you are seeing here is that, well, you have one indicator for free, and that's the temperature. Maybe it's not the best, so that's something to look into. But what you see for those annealing metaheuristics, there's no need to make some very complicated, complex indicators. Just use the temperature. It makes sense. It's understandable. And I think it's also easy for your storytelling. So I think these two aspects, so reusing, I think is helping. So that's, let's say, becoming more sustainable. Using this kind of free indicators is helping you. And if you, in that way, also, let's say, find better solutions for your optimization problems, if you have a better solution for your optimization, it's reducing, for example, waste, and that's also becoming more sustainable.
Okay, that's clear. Thanks. I know that's a work in progress, so let's see, in the future, what this work brings as well in end of domain. So at this point, I'd like to thank you very much for your presence today, although you're a regular in those webinars. So thanks for being today on the other side. Before closing, I'd like to share my screen just to show what's planned for the coming weeks. So please hold on and give me a second. I'll try to share my PowerPoint. All right, so that's what we have planned for the for the coming weeks. So next week already we have a presentation by our colleague Leon Homans on Amsterdam Data Exchange. February 22nd, using AI on flight simulator to support evidence-based training. March 8th, structured machine learning, and March 22nd, it's planned deep turnaround insights from Schiphol. More webinars are in the making. Let me go back to my screen. So, thank you everyone for being with us today. It's been a pleasure, and see you next week already. Thanks a lot. Have a good evening.